welcome to the building tour Allegra in Luxembourg. My name is Wojciech Niedzwiedz. I'm a senior building services consultant and I will be your tour guide today. We'll be using those HoloLens 2 glasses, so you will be able not only to see the building itself, but also some augmented reality images that we've placed to make it more interesting and interactive. We'll start our tour here in the office of CDCL, who are the general contractors who built that project Allegra, and they're also our licensed partners in Luxembourg. After the brief introduction and explanation about the building, some data and facts, I'll move over across the road to where the new project is being now completed, and then we'll come back to Julia and open the floor to you. Hopefully you will have lots of questions and we'll be able to answer most of them, if not all of them. So without further ado, let me put the HoloLens. We'll switch them on. And I will see you very shortly from the other side. Now you can see what I see through the glasses. You can also see the augmented reality object that we've placed here. Let me put it in context. Here on the left, you can see the existing building in which we are at the moment. Back in 2017, CDCL were considering looking for different ways of construction using prefabricated technology and using renewable resources. And that's how we started our relationship with CDCL. After a number of meetings and conversations and their visit to our office in Austria, they realized that CREE could offer viable technological solution. So we created this 3D model to represent how the existing building would look like if it was built with CREE. And that led to creating a cost estimate, which the bottom line was showing that if the building was built with CREE elements, it would have been about 4% more expensive than the traditional construction. Now, this didn't take into consideration a number of factors, like, for example, that the building CREE system would have been completed 4 months earlier. So obviously that's a huge benefit to the owner of the building to be able to rent the space 4 months earlier. Also the carbon tax savings because of use of renewable resources. But other factors which are difficult to measure in non-monetary terms, like CO2 savings, the carbon footprint savings, the fact that the elements are prefabricated and therefore the quality and precision is much greater than building on site. And also health and safety aspect, obviously there's less potential for accidents happening on site rather than having them pre-manufactured in the factory. So at that time, CDCL were considering building their new headquarters, and it was an obvious choice that they would go with CREE system and design their new offices with CREE. They've appointed an architect who created that image, how the future offices would look like. And in fact, this building is nearly completed, and CDCL will be moving into it, and they will be occupying the entire ground floor, and the upper floors will be up for rent. Whether the reality meets the architect's expectations, I will let you be the judge of that, because if I move across the room, come closer to the window, here you see the Allegra building in its full glory, with the only difference being a dark sky on the November day. But other than that, I believe the architect will be very pleased with the final outcome. So I'm going to take you over across the road and show you the building inside. But before that, let's have a look at the plans of the building so you have an idea of the size and geometry. So as you see, the building is based on a regular grid, 2.7 by 2.7 meters, which fits perfectly to the CREE slab elements. It consists of two separate almost buildings, the north and the south wing, joined in the middle with a huge open plan lobby with the staircase and elevator shafts. Each half of the building has its own center core with additional staircase, toilets, washrooms and mechanical service risers. As I said, CDCL will be moving to the ground floor. the remaining floors look almost identical. There's only a slight difference on the ground floor. There's a setback, the first two grid lines creating like a canopy overhang. And on the top floor, there is a cutback as well, and there's a terrace facing the Luxembourg city centre, so it's a nice view from the top of the floor over there. The building consists of 4 floors above ground, and there are also 3 stories below ground for the car parks, and there's also a gym or fitness studio in the basement for the employees. Now, one of the reasons why this project is such a success story is that the CREE design was considered at the early stage. So the building is based on the regular grid. There's a huge amount of repeatability of the same elements. And the fact that the mechanical engineers, architects and structural engineers were working on this project and were involved from the very early stage of the design. So if you think about this, the 3D model was created not only to provide the coordination between all those trades, but also it's very easy, once the model is created, it's very easy to split those elements. If you think about all those elements have been created using Revit families, which are available on our platform. And it's very easy to create a schedule with quantities and then also calculate the cost of the project. So that's another benefit of this digital twin that gives you the cost certainty. And if I take this image away and show you the typical floor plan split into number of different slab elements, if you disregard some smaller cuts for mechanical services, there were only 4 different types of slabs required for that building. And if you consider this 1,212 slabs altogether and some 250 columns, that's really huge amount of repetitions, and that's what makes the project financially viable. The 3D model was also created to show the phasing and the sequencing of the construction and assembly. So here on this image, you can see that we're using one tower crane and one mobile crane. The tower crane was used to lift all the wall elements and the concrete core, and the mobile crane was used to lift all the slab elements. Typical wall elements is about 3 to 4 tons. The slab elements, 7, the heaviest one, the corner ones with the concrete edge beams, about 8 tons. So that was the first phase when they erected the concrete podium and the concrete core. And in the next phase, the north part of the building was erected. And the interesting story is that it took about 9 weeks to erect that part of the building. There were many reasons for that. It was longer than expected. The main reason was adverse weather conditions. You may remember in summer there were terrible floods in northern Germany, and also affected that part of Benelux, and the torrential rain. So the construction site had to be stopped for some time. That we were in the middle of the pandemic as well. And also one of the factors was the delivery that was scheduled to bring the slab elements was 3 trucks per day. Each truck can take 3 elements, so they had 9 elements per day. And as they were progressing with the installation, they realized they can install those 9 slabs within, say, half a day, so the other half a day wasn't that productive. So they had to rethink how to reschedule that in the next phase, and that's exactly what happened. This is the 3rd phase of the project when they erected the south part of the building, and it took them almost half the time they were able to save during the construction. So it's about 4 weeks this part was completed. They were using 2 teams of 4 people plus the crane operator. The first team was responsible for bringing the elements and putting them in position, with the second team to follow joining those elements and filling the joints with the mortar. All the wall elements came from Trier, which is across the border in Germany, not far from here, whereas the slab elements were shipped from Bremen. That's about 500 kilometers from here. And despite that significant distance, it was still financially viable and commercially viable to ship them from there rather than find a local manufacturer in the area. So now I think you've got enough sort of background information on the building and the story and our collaboration with CDCL. I think it's the time when we move across the road and I show you the building inside. So again, I just need to put my safety shoes because it's still construction site and my high-vis jacket and helmet, and I'll see you on the other side. Now we are inside the Allegra building. We're just walking onto the second floor. You see lots of construction activities are still happening. The fit-out in the south part of the building, we unfortunately can't access there, but we've been given access to the north part of the building. You see the raised floor already installed. There's relatively few activities happening. On the opposite side, the space was already rented out, and that's why they are fitting out the interior partitions, floors, and finishing the MEP services. You see here, MEP services are pretty much completed. One thing missing will be a bulkhead to cover all those services in the middle, but you see all this exposed timber. You see the timber beams and load-bearing columns. One thing that's very difficult to describe is the smell of wood, and despite the fact it's still a building site and a little bit of dust around, you can really smell the wood. I can imagine it would be a very nice atmosphere for people working here. The building spans about 40 meters across and 16 meters wide, and you can imagine it gives huge flexibility for the interior designer to design the internal layout to suit any particular tenant. From the structural point of view, the building is well balanced. It has a central core that provides the stability in the vertical plane, and because of the wall being separated quite far from the central core, additional stiffening was required, so the architect opted here for this diagonal column, which looks very nice and fits the character of the building. You can see a typical grid that spans from this point here across that point. That's 2.7 meters. You can see the concrete beam at the back, and it goes across 8.1 meters to the middle girder, and it's supported on that middle girder, which unfortunately we can't see it right now because it's already encapsulated with gypsum boards for the fire protection. For those of you who are familiar with CREE System, I don't want to spend too much time describing how it works, but we have prepared this 3D model representing the idea. So you've got load-bearing columns here with the steel pins, and on the other hand, it represents the central concrete core with the L-shaped steel bracket fixed to the wall, which provides the support for the other side of the slab. So the slab has a cutout in the timber beams here, which are resting on that bracket, whereas on this side it's a edge beam with the openings which sit directly on top of the steel pins. I'll try to position as precisely as I can. You see that slab fits directly on top of those pins. Obviously it's not scaled, but you see on the other side it should fit to the top of the bracket. There's another slab we've got here. So again, you see the cutouts in timber beams on the left-hand side, and the ring and the edge beam on the other side. So again, let me try to position it. Once the first slab is installed, the next one is being positioned adjacent. Again, I need to move back in order to be able to grab it and try to position it as closely as I can. I think the crane operator would have done a better job, but I think it gives you an idea how it works. So once the two slabs are positioned next to each other. There is a small gap in between them, and that's where we've got a shear connector, and then the gap is then filled with grout. I think we've got another example of another type of connection. Again, the wall connected to the load-bearing columns, slabs, and the middle girder. So again, it's the same idea. There are openings which are not shown on that particular element. So this portion of the concrete that projects over the timber beams has openings which would fit directly into the pins on top of that middle girder, and that would sit on top. And again, the next slab is positioned adjacent to it. And there you go. So it's as easy as putting virtually Lego blocks together. Typically, it takes about 20 minutes to crane one of those elements and position them on top. And as soon as they are positioned, the second team would come and would fill the gap with the mortar or grout. So that's how the system works. When it comes to the wall elements, all of them were prefabricated in factory conditions, so not only the outside, even including the additional timber buttons, architectural sort of features, but also the inside with the seals, windows, and the gypsum board. That was all prefabricated and delivered in one piece. So another fascinating detail about that project was that for the first time we didn't have to use the external scaffold towers when the elements were put together. There was obviously an issue of protecting them from the weather. As I mentioned, there were terrible weather conditions back in summer, but I'll show you a few other slides to explain how that was taken care of. But the fact is that for the first time we didn't have to use the scaffold tower. That gives us also an idea for the future how quickly the buildings can be erected. We've got a few slides prepared for you to show you the whole sequence, how the wall elements were assembled. So as I mentioned, this one shows the setup in the factory. The elements are built. Here you see it's only the gypsum board missing, and they will be ready to be shipped to site. If I have a look at this picture, shows concrete core being already completed, and the first elements, wall elements, are being delivered to site and hoisted into position. So the first phase of the project was, as I mentioned earlier, was the northern part of the building, the northern wing, and you can see the first elements being assembled, positioned on the ground floor. You see they're already protected with some plastic sheeting, and you see lots of water on the floor. Obviously, that the weather conditions that day weren't great, but still they were managed to protect the wall elements. Here you see the second floor being built, and for example, the entire corner element is delivered in one piece just to avoid the joints on the corner, and each single element had carefully planned joints which were behind the columns, so they fitted perfectly next to each other, and as I said, no scaffold was required afterwards. Here you've got an example of how the ceiling slabs were lifted and put in position. So this is what I mentioned before on our 3D model. You've got this concrete portion projecting over with the openings, and they fit directly on top of the steel girder. Here you've got another panel being lifted and positioned, spanning from the wall to the middle girder. And what I mentioned before, once the two panels are put together, there is a gap between, and what we use in this particular project was this shear connector, 10-buckle connector, which just adjusts the position of two slabs, and the gap between the beams is, between the slabs is then filled with grout. And that's when the north building was nearly completed. We already started the south part. You will see that that's the only part that wasn't fully prefabricated was the top floor. The reason being is because of this parapet wall overhanging onto the roof. It was over 3 meters high, so we weren't able to manufacture it in one piece because of the delivery constraints. We weren't able to take elements over 3 meters high on the lorry, so that's why this element was split into two sections. So the parapet wall was installed as an additional section, and that's why those timber buttons weren't installed in factory. They were fixed from the cherry picker afterwards. And here you go, nearly completed building, north and the south wing, completed timber battens already installed. Now all the works were concentrating on the core, fitting the glazing, the curtain wall. Very often in our virtual tours we concentrate on the architectural and structural details of the building. But because of my background being an MEP engineer, I wanted to talk a little bit more about the MEP services, because I find it fascinating and very interesting solution that was adopted in this particular building. Those who are familiar with the virtual tools from IZM and from LCT1 would probably realize that the gap between the timber beams is typically filled with mechanical services, and then it's covered with the radiant panel. So all those services would be hidden from view. Whereas here, you've got exposed concrete and only sprinklers and the smoke heads are visible. So if you're wondering how the heating is provided in that building, it's because we're using thermally activated concrete. So the concrete slab that you can see just directly above, there is a capillary tube, capillary mat installed during the prefabrication process, and when the slabs are being delivered to site, the only thing that you would see is like here, those two white pipes for the flow and for the return of the water. So how the heating works in that building is in summer, when all the thermal energy in the building that comes from the solar radiation, from people inside the building, from light fittings, computers and any other electric equipment, it's absorbed by the cold surface of the slab, and the water flowing through those capillary tubes dissipates that heat back to the heat pumps in the basement and down to the ground, because there are not 38 boreholes, 90 meters deep each, which then act as the geothermal energy source for the building. And the same in winter, the warm water flows through those capillary tubes, heating the concrete, and concrete being very good thermal energy storage, mass storage material, radiates that heat, warms up the surfaces and the people inside. So this is very energy efficient solution. Other benefits is obviously the temperature spread across the space is very equal. There is no noise from any mechanical parts moving, and it's very inexpensive for the maintenance purpose. When it comes to ventilation, the air handling unit, which is located on the roof, brings the fresh air, tempered fresh air via the heat exchanger, and that goes in the riser vertically down the full height of the building, and then comes to each floor. And you see here ventilation ducts for the air supply on both sides, and in the middle the return air. So there are outlets from the supply. You can see in the future that will be covered by the bulkhead, but it will be still almost 2.5 meters headroom below the bulkhead, so the fresh air will be delivered between the beams across the space and will be returning from underside of that bulkhead and back to the air handling unit. You see on the mains water services for the cooling and heating, ventilation ducts and the sprinkler pipe. And as I said, this all will be hidden in that bulkhead. Everything else will be nice, clean finish, and only the sprinklers will be between the timber beams. The entire building will be very energy efficient. It will comply with the NZEB standards, which is nearly zero energy building standard. It will have a BREEAM certificate Very Good and Energy Performance Certificate A, which is the highest in its class. And all this will be controlled via BMS system, bespoke BMS system. Now, when we talk about the BMS system, there is one thing I wanted to mention. CDCL and CREE are part of the research project called Project Sphere, which is just sponsored or funded by European Union. And the reason for that project is to develop a digital twin and provide some digital tools which could then monitor the energy consumption of the building and analyze it and hopefully find ways of improving how the building can be run in a more efficient way. And we are participating in that project. What will happen soon, once the building will go into operation in January, we will connect the BMS system to the Spheres platform. We'll be able to transfer all the data from the sensors, and then we'll be able to monitor and test those new tools, and we'll keep you updated on any outcome. So this is really a big thank you both to CDCL for allowing us to taking part and using their building as a test pilot project, and to the Project Sphere participants as well. The way that the building is divided from the BMS point of view, each floor is separated into 4 quarters, so potentially can be sublet to 4 separate tenants, and they've got separate meters which can be then controlled and monitored, and energy can be billed directly to those tenants. There's one thing also to mention. There is an array of solar panels on the roof which are able to generate about 27,000 kilowatt hours of additional electricity, which can supplement the ongoing running costs of the building. And there is also a potential for expanding that PV array on the northern part of the building. But one of the tools from Project Sphere, for example, will be able to establish that additional energy generated from solar panels, and we'll find out whether it's viable to add additional panels, whether that would bring any additional profits. Before we finish, I just wanted to show you a few examples of how they dealt with the adverse weather conditions they had during the construction. I mentioned a few times about this problem and how they dealt with it. You can see on this image, they placed the plastic sheeting covering completely from top to bottom the entire wall elements, which were prefabricated off-site, obviously, so not only the timber columns, but the gypsum board, the internal layer finish needed to be protected as well. So this plastic sheeting was then tucked on top of the wall and fixed with the edge protection that held it together as well, to make sure that no rain is getting into the middle part of the wall where the insulation is. And then when the slabs were delivered to site, the edge protection was removed bit by bit, and the slabs were able to be positioned between the wall and the middle girder that you see on that picture. Also, once all the slabs were positioned, let me bring this picture a little bit closer. once the slabs were positioned, you see the grout was filled in, and also the green protection tape was placed on top, just to make sure to let the grout settle before the rain could get in contact with it, to make sure it's protected that way. And also you'll see the protection on the edge. There's this black plastic foil was placed to make sure that the rain doesn't get into the middle of the wall. And before I finish, I'll just look across the street to see the existing offices of CDCL. They will be moving very shortly. They're very eager to move to the new premises. During Christmas time, between the Christmas and New Year, the removal truck is coming to take all the furniture and relocate them to the new premises across the road, and they will all get a very nice Christmas present. When they come back from the holiday, they will be in the new building. Sadly, this is the end of our tour. Just wanted to remind you that there is a chat on the right-hand side of your screens. Please ask any questions that you may have. I appreciate we only covered very briefly lots of subjects regarding this fascinating building, but we hope that Julia and her guests will be able to all the questions that you may have. So I will just have the last final look at the building, and I leave you with a thought. Can you imagine your next project being a CREE project?